inaugurated in 1955, and I was assigned, I went transferred into what was called large engine development, and I was transferred to this area in 1955, although I worked in the office buildings where we started out. This test stand was, as I said, was originally set up and tested the Atlas engine for the Atlas missile, which was an ICBM, an intercontinental ballistic missile. The test stand was more advanced than the one you saw in the video. This one had a flame bucket. In other words, if we could pull this grating back, you notice there's little tracks here. That grating rolls back, the engine was installed there, and the flame bucket is a chute that's bent out, a chute that goes out into the canyon area. The Atlas, as I said, was originally designed as an intercontinental ballistic missile, but was later used to launch commercial satellites. It consisted of what was called 3 barrels, 2 booster engines, and a sustainer. Each booster developed 150,000 pounds of thrust and fired for about 5 minutes. The sustainer engine, the booster fired over about 2 minutes, and the sustainer, what would happen is all 3 barrels would light off at the same time. The Atlas would be launched, and after about 2 minutes, the boosters would slide down rails, fall into the ocean, and the sustainer would continue with the missile all the way to the target. About, it could go like 6,000 miles. The test stand was designed, if you will, to simulate the missile. The top tank contained the liquid oxygen. The lower tank contained the fuel, which was basically kerosene, a high-grade kerosene called Rocket Propellant 1, or RP1. Unfortunately, you can't simulate missile flight with a static test stand. There are dynamic forces that take place during a launch that you have to find about later as you launch. The engine that you saw in the videos was the Redstone, which was an upgrade from the A4 engine that the Germans used in the V2 missile. And bringing the Germans over here probably saved us about 10 years. But this was a contract that North American picked up to start. Well, they started building the Navajo back then also, because they were no longer building airplanes for the war. So these rocket engines were built by airplane designers who didn't know beans about rocket engines, and of course they used aircraft design techniques in their fittings and things like that. They would bring the engine from the Slauson facility, which is where they were building the airplanes. They'd bring it up and put it in the pre-test building up there. There was 2 groups in operation at every test facility. The development group that I was in and the test group. The test organization had the responsibility for prepping the engine, providing the instrumentation, and operating the test stand. They did a magnificent job. There's a lot of problems connected with this that we don't give them enough appreciation for. But they had the job of making sure that the test facility was operating. The development group, that was me, had the responsibility for defining the configuration of the engine to be tested, the type of instrumentation that was to be used, and the nature and duration of the test. We had the responsibility of filling out, or I did, that test request, signing your name on the bottom, and turning it over to the test group. The problem was, in those days, trying to get the perfect combination of flows of the liquid oxygen and the kerosene, because the engine was sold to the Air Force on the basis of thrust. It had to meet a certain thrust. It had to perform with a certain mixed ratio of propellants. In other words, the amount of oxygen relative to fuel had to be predetermined and it had to be precise, because the tanks of the missile had a certain quantity and they were designed for an optimum mixed ratio. We also sold it in terms of of course, the weight of the engine was specified, and what was called the specific impulse, which is the amount of thrust you get for the amount of propellant you use. And as the years go by, rocket engines got higher and higher specific impulses, or ISP. Anyway, the engine would come in from Sloss and go to the pretest building. They'd start installing instrumentation. Then they'd bring it out and they would do electromechanical checks. They would run end-to-end calibration checks of the pressure and temperature and vibration and so forth. Measurements taken off the engine that was sent to the control center. Now the control center appears below ground. The one you saw in the video was Bowler is above ground. All the other control centers are below ground. Some of you can see it, you can look at it later, and Art will point it out as we drive back. There's a structure, a low structure front. You see it's dark, it's black. That was the top of periscopes. The test engineers, or whoever's in the control center, would be watching the test through the periscopes. By the way, they also have little pillboxes there. You may see them up in the rocks, where they put a test engineer or test mechanic with a cutoff button, and he'd be watching the nature of the flame, and if something looked unusual, they'd cut it off. So anyway, they bring the engine out, install it on the test stand, and do all the hookups, the electromechanical checks, and the end-to-end instrumentation checks. After every test, and the original test might be just a short, what they call transition test, and then maybe a short main stage test. But we were very cautious. We worked our way slowly up to getting full duration main stage tests. But after every test, they'd have to flush the engine because there might be blowback. In other words, when the valves were shut down, there could be residual pressure. It would blow fuel, kerosene, back into the liquid oxygen passages, and that's a no-no, because liquid oxygen in the presence of any carbon material, you guarantee a fire or explosion. So how did we do it? They would hook up and inject trichloroethylene, which was the solvent of choice in those days. Everybody used it. In the valley, they used it for gas stations everywhere. And they'd have to flush out the liquid oxygen passages. That trichloroethylene was allowed to go down into the flame bucket and into the settling pond where the water from the flame bucket would go. So that's in the soil, and Art will tell you more about that. That big tank you see to your right, standing by Art, is the trichloroethylene tank. Because if liquid oxygen came in contact with kerosene, it forms a gel. It looks just like kind of a little gray-brown jello, which was shock sensitive like nitroglycerin. So you can imagine, like for example, I've heard stories where mechanics would always go in, the test mechanics would go in after a test to check for burning in a combustion chamber. And sometimes they'd see this little pool of gel on the face of the injector. And so he'd very carefully get down and not touch anything and get out. So we'd flush it with trichloroethylene because it said you had to in those days. Otherwise, you guaranteed explosion. Sometimes,
was there ever any accidents of any explosions or anything? Were there ever any accidents, any explosions?
We had, people ask that question, do we ever have explosions? Yes, many, many times. They'd blow the engine right off the stand.
Wow.
The test stand would remain, but they'd have to repaint it and rewire it for the instrumentation. But yet, in those days, there was many explosions. It's quite dramatic. Now, the critical problem that the development people had was I'd get data. You saw those charts, for example, in the video, they were tapping these round, those are called direct inking graphic charts. They would pull those off after every test, arm loads, and dump it on our desk. And we'd go through looking at the data, trying to figure out if the pressures and flow rates within the engine were correct. And we would do it by a trial and error process. Nowadays, they have what's called engine balances, where they put all the characteristics of the engine and the liquids into a computer program, run it, and it tells you what the flows and pressures are throughout the system so that you can make adjustments rather quickly. In 1955, we didn't have computer programs. We did not have computers. But what we did have were not bound notebooks or charts. And this is slide rule. This is the Ferrari of slide rule. This is the Kufel and Esser log duplex decitree. And it works very easy. Like, for example, if I multiply 1600 times 21, it's 3,660,000. There it is. You can see yourself. The downside is it doesn't give you the decimal point, but you know that if you've done the problem. And the upside is it doesn't take any batteries. Now, the Atlas missile, as I said, was an engineering marvel. You can put it. I'll show you here. In 1958, if I had bought a Revell plastic model of the Atlas, it would have cost me about $15, and I should have bought one. Now they go for $250 on eBay. But I got this. This was from the Philippines. This is $68. This is a model of the Atlas that this engine went on. There's the three, the two boosters and the sustainer. This was 75 feet tall and 10 feet wide. And when it was loaded and ready to take off, I think it was 267,000 pounds. And of course, the engines were developing about 360,000 pounds of thrust. As I said, this was an engineering marvel because, like the German V-2 had a fuselage and the tanks were inside. On the Atlas missile, they had no fuselage. The tanks were the structure. The stainless steel tanks were 2/100 of an inch thick. The skin. This missile could not stand up of its own weight. They had to keep it pressurized at all times. Wherever it went. When they first built it, when they transported it down the highway to wherever they're going, they even had they carried extra helium trucks along. If you ever saw this parade going down the highway, I always think of it like a Coke can. It's very thin, and in fact, one of these Atlases blew up at Edwards Air Force Base. Walt Greenwald and I were sent back out there. It's just sometime, could have been 1957, to pick up the pieces of the engine to see whose problem it was. It was the engine problem, but I picked up a piece of the tank. This is what that material is made out of. Wow. Stainless, you know. I picked this up off the ground. You can see it was kind of burned. Anyway, John Glenn, in 1962, in his Friendship 7 capsule, sat on the top of these and became the first American to orbit. He was really gutsy. Yeah. Is there any questions so far? Anything?
What kind of engines were they when they first started here?
The engines at first?
Yeah, what kind of engines?
Well, starting with the Redstone, all the engines consisted of a flat injector plate with tiny holes in it, with channels in the back where the liquid oxygen and the RP, the kerosene, would be injected like a spray from in your shower and ignited. And there was a combustion chamber and then an expansion nozzle. The Atlas used what was called, from then on, all the engines were this way, tubular wall thrust chambers. They consist of like a stainless tube that comes down to a manifold and the fuel comes back up. So the fuel running down the tubes and back up cool the chamber. Otherwise, it would melt. And the fuel is retained, so it's called regenerative, cooling. The flame coming from the rocket engine is 6,000 degrees Fahrenheit. That's hotter than the boiling point of iron. That flame would go down into the flame bucket, and of course they would pump tens of thousands of gallons of water a minute in the flame bucket to cool it. Because if that water was ever interrupted, even momentarily, that flame would melt the flame bucket just like butter. And that sometimes happens. But we'd run these tests. The test group would bring over the data, dump it on our desk. we'd decide if we were getting the flow rates and pressures and thrusts